feel like that's a new announcement that's happening these days. I don't know. Anyway, all right, so last section, 6.3. We talked on last week about how we could do a little review about area between curves, our disc or washer method. I saw a lot of great answers on that discussion on that was due on Friday, just sort of like talking about strategy and decision making. And then we talked a little bit about, well, what if the methods that we already know aren't actually applicable to a situation, right? And so we showed a very classic, I would say this is a very classic picture of a situation where using the methods that we know about disc and washer method don't actually help in this case, okay? And then we talked a little bit about the name, this name that like when someone calls something shell method, we as especially as Southern Californian folk might be thinking, ooh, like a shell. Anybody get a chance to watch the Marcel the Shell video? I think there's like 3 of them. Did you watch the one where he has like his pet dog on a string, but it's really like a piece of lint? Or did you watch a different one? Yeah. Anyway, if you need some sort of like brain break over the next few days, check out the Marcel the Shell video. I think it's pretty cute. But what we ultimately arrived at is when we're talking about shell method. Oh, I'll have to check that one out. Okay. When we're talking about shell method, we're really thinking not about seashells, but really about this idea of these really tall cylinders. And they're very, very thin cylinders that you can then sort of nest inside of each other. And so when we thought about our 2 pictures here, right, we said if we have washer method, then this line represents the radius. And I think most of you got that on the discussion, which was awesome, okay? But this line right here, it doesn't represent the disk, it actually represents the radius, okay? And so I think I saw a few folks who said that that line represents the disk, but it actually represents the radius, okay? Whereas when we're looking at the shell method, the same line that we draw actually represents something completely different. In fact, it represents the height of one of those cylindrical shells, okay? And so you have to be really careful. Yes, you can draw purple lines, but in different scenarios, they're going to mean different things, okay? We took a look at a computer generated diagram, which was far better than my individually nested cylinders, right? But the cool thing about the cylinders, like why would anyone choose this shape? The reason why they're choosing this shape is because when you take a single shell and you unravel it, you end up with a rectangle. And rectangles are a nice shape for us to find the area of. And so we were able to say the area of this is going to be 2 pi r, which is sort of the length times the height, which we called lowercase h. Okay. Now, I think that this little diagram right here, this graphic organizer, is probably one of the in my opinion, more helpful things as you're sort of trying to learn all of this and cram it for this exam that's coming up, is thinking about, you know, what do these things represent and how do we set them up? Okay, so when you're looking at a question and you're feeling unsure about how to make those decisions, I would come back to this chart to maybe help you out a little bit more, okay? I think one of the most common mistakes is that sometimes we're not sure whether it's going to be dx or dy. And so it would be really important to make that distinction, okay? And so with that, let's jump into an example, and let's see how many examples we can get through today. That is sort of the goal. And here we are. All right, so example 1. This is the question that we saw last Wednesday that we were like, we don't know how to solve this one, okay? So it says, determine the volume of the solid obtained by rotating the region bounded by y equals x minus 1 times x minus 3 squared and y equals 0 about the y-axis. And so we've got this diagram right here. We've got our axis of revolution, okay? And this time, we tried already like drawing our purple lines this way, right? We tried that and we noticed that the issue was if you are trying to do right minus left, it's actually the same curve, and that makes it very difficult to find the definitions of the different curves, okay? And so if we look at a picture, all right, so this is sort of the 3-dimensional pictures that are help us visualize things a little bit more. If anyone here has ever had a bundt cake, anybody here ever had a bundt cake? Right, there's even that company now, Nothing Bundt Cake. Yeah, which are really good, by the way. They're cream cheese frosting. I don't know what they put in it, but it's really good. Yeah, and so a bundt cake, this is sort of the shape that we're looking at right now, okay? And so for those of you who are thinking about doing math and writing assignment number 8, where I'm asking you to create 3-dimensional objects, it could be that you are thinking about some sort of food might be something that would be easy to slice into both discs and shells, right? So if you are someone who likes to bake, I know some of us love to make cookies in here, then maybe that could be something where you're thinking about using that to help you with the equations and finding the different slices, okay? All right, so we've got this shape here. And what I really like about this second diagram is they do that symmetry thing that I've said is sometimes helpful, right? This is the original curve. And then they did like the symmetrical piece on the other side, okay? Well, that is sort of the beauty though. I think it's gonna be a lot harder to find that volume, but you can cut it into different shapes, right? I wouldn't serve it that way though. Maybe that could be the new TikTok trend though. I don't know. Okay, and so what we have here when we're looking at this, we could have washers, but what I'm going to do is I'm going to go ahead and draw in, I'm going to take this diagram, I'm going to draw sort of the reflection piece, and we're going to take a look at what it looks like when we draw the shells in. All right, so let's keep the curve red because that's what they have. Look something like this. This is 1, this is 3. And so I would have something similar on the other side. Yeah, close enough. Okay. Now, if we wanted to think shell method, all right, we can pick any sort of line to be our purple line. Now, for our purple line, though, if we're going to use shell method, what relationship does the purple line have to the axis of revolution? Exactly. Great, Marissa. Great, David. We want these to be parallel, right? We want these to be parallel to that axis of revolution. And so when we draw them, let's pick like this one right here. All right. If I drew that, that purple line would represent the height of one shell. And so where is the shell? Well, sort of looks something like this. And so we've got one cylinder. Okay, now remember that cylinder is hollow. In fact, it's so very thin that it is essentially as like thinner than the sheet of paper. Okay. Now, just like we have an infinite number of discs and washers, we also have an infinite number of shells. And so let's draw another shell. And for clarity, I'm just going to use a different color. Okay, so I'll do this one in green. But let's say I have a shell here, that green line. Is this shell going to be taller or shorter than the purple one? So is this green shell going to be taller or shorter than the purple one? I agree. I think it's going to be taller. And is the radius of this cylinder going to be bigger or smaller than the purple one? It's going to be bigger. Good. And so if now we draw in that second piece, that one is the green one is definitely taller than the purple one, and the radius is bigger. Good job. Good job. All right, let's try one more here. Let's maybe do a blue one. What if I have a shell and this blue line all the way out here is the radius of that shell? Is this shell, the blue one, going to be taller or shorter than the green one? It's going to be shorter. What about in comparison to the purple one? Taller or shorter than the purple one? It's also going to be shorter. Good, good, good. What about the radius of this blue shell? Is it going to be smaller or bigger than the ones we've seen? You got it. It's going to be bigger. Okay. And so if we sort of draw this in, we've got this other height out here. Ooh, it's going to be a really sort of wide one. Um, and so we've got this very sort of squat looking cylinder all the way towards the end, right? And so we've got a purple one, a green one, and a blue one. And each one of those, in between them, there's actually an infinite number between those, okay? And so when we think about our setup here, what would be really important is to go back to our chart and say, should we use dx or dy, okay? Now, before we go back up there, let's keep in mind a few things. Our axis of revolution, y-axis, okay? And looking at this equation, y equals x minus 1 times x minus 3 squared, do you want our shell method to be dx or dy given this equation? Like, what would make your life easier? Yeah, I think dx is actually a really good choice. Can you imagine if someone was like, take this equation and get x all by itself? Like, that sounds miserable. I don't want to do that. So let's hope that the setup here is going to be dx. Okay, so let's go back up to the top. Let's take a look at our shell method. So we've got shell method. And let's look first for our axis of revolution. That in itself actually tells us quite a bit, okay? So we know we want shell method. We know we have a axis of revolution, that's the y-axis. And our slices, our lines are parallel to the axis of revolution. Excellent. We have all of those things. That means we get to use this formula. Volume equals 2 pi the integral from a to b of radius times height dx. Thank goodness it's dx, right? We can also see from our picture that those shells that I drew are sort of standing up and down like this. So once you've drawn your picture, okay, I think this chart is very hard to use if you haven't drawn your picture yet. So once you've drawn your picture, go to the chart, see which one matches, right? So let's grab this formula. Volume equals 2 pi the integral from a to b, radius times height dx, and let's apply this to our question. So volume equals 2 pi the integral from a to b of, I'm going to write it out in words, radius times height dx. Okay. Before we move on, does it make sense why we chose the formula we chose? The 2 pi radius times height integral dx. Okay. That would be a really important thing to go over. Maybe at one of the tutoring sessions, if you plan on going, just kind of practice picking equations. Like, what if I have this picture? What if I have this picture? What is this going to be? Okay, so I think having the chart is helpful, but only helpful if you know how to use it, right? Okay, so now let's plug in some things. So when we think about our dx, since we have dx here, that means that this radius and this height should all be equations that have x in it. As long as it has x in the equation, then we're sort of using the right one, okay? So let's go back up to our diagram for a moment. I think this one is a little messy, the one on the right-hand side, but this green line was like a height. This purple line was a height. This blue one was a height. And the function that defined all of those heights is the one that they gave us. X1 minus 1, x minus 3 squared. Okay. So this is a y value. This is a y value. This is a y value. And they're all y values that make this equation true. And so what we're going to do, this is sort of like the kind of problem where I wish we were back in the classroom, because even though we can like visualize more things here, I like to be able to write on all the boards. So that kind of makes me sad. But if we have our 2 pi, and let's leave this for right now. I know that the height is going to be a y value. And that means that our radius, like that's a radius, those we could call x values, right? Because they're horizontal here. So I'm going to take one intermediate step that we haven't really done here so far. Instead of radius, I'm going to write x values. And instead of height, I'm going to write y values. Okay. Does that make sense to folks why the radius is an x value? Okay, and the height is a y value because it goes up and down. Okay, all right. So now let's do this. The y values, we know we're going to replace with this gross looking equation. Okay. Let's ignore my sort of very messy diagram for a moment. And let's kind of go back to the original picture. If I had a shell right here, okay, so sort of the shortest shell with the smallest radius, what is the radius of this shell? You know, like if it sort of went like this, what's the radius of that shell? Good. It's 1, right? It's not the diameter. We're looking for the radius. Okay. What if I had the shell that went, you know, sort of off my page, but went like this? What would that radius be? Good. Yeah, it would be 2. Excellent. Okay. What if I had a shell that was like right here? That was the height. What's the radius of this shell? Nice. Yes, 2.5-ish, right? And tell me this, what is the biggest radius that a shell could have in this picture? Oh, 3. Someone tell me, how do we know that the biggest radius is 3? Yeah, we could think about them. It turns out they are our bounds. But if we look at our picture, we're only choosing exactly. That's where we're saying we want it where it crosses with the y equals 0, that x-axis. Yeah, exactly. That's the last place they cross. So that's going to be the biggest shell. Well, it'll be the one with the biggest radius, right? Okay. So of all the ones that I just asked you to like, tell me how big this radius is, what was the smallest radius that we had? 1. And what was the biggest one? 3. Okay. You folks have just found our A and our B, our bounds. So we have A to B, and they are exactly like you folks said, the smallest radius is going to be 1. The largest radius is going to be 3. Okay. Now let's fill in our equation here, and I'll tell you what we're going to put in here. 2 pi, the integral from 1 to 3. Every time I looked for the radius, it turns out that it was exactly the x value of where I was. Meaning, I said, what's the radius here? And you all said 1. I said, what's the radius like here? And you all said 2. What's the radius here? You all said 3. Those are exactly the same as the numbers down there, which means they are exactly the x value. So I'm going to just drop the values and I'm going to say that the radius is x. So this radius corresponds to the x values. Now, how do I know not to pick an x value of like 0? Because that would be inside of my bundt cake, that space where there's actually no cake. How come I never get a 0 out? Or how come I never get a 4 out for the radius? What have I done already in the problem to make sure that I don't get 0 or I don't get 4? the bounds. There you go. These bounds, right? This tells me start counting at 1, stop counting at 3. So I don't have to worry about all the other x values I don't want. I only want the ones between 1 and 3. Well, then we just need to fill in our height. All right. So our height is going to be the equation that we were given in the beginning, which is just x minus 1 times x minus 3 squared. And for good measure, I'm just going to put brackets around this so we can see that separately, this is the height. Okay. Absolutely. So if I think about all of the shells that we drew, right? Every single one of them had a radius that actually corresponded directly to the x value. No, I love that question, David. Hold on to that for 1 second. Okay, let me answer Thea's question, then we'll talk about like what we're going to see in the context of this class and what you might see in a different class. Okay. So if I said, what is the radius of this shell? Then I think we would all agree that it's 1. And see, that happens to be the x value right underneath it. If I said, what is the radius of this shell? We might say 1.5. And that also happens to be the x value right there, 1.5. If we look at the radius of this shell, we would say it's 2. And 2 happens to be the x value down there. And let's say we pick this one, we would say this has a radius of 2.5, which if I wrote out all the numbers, it would be 2.5 down here. And then the very last one has a radius of 3. And that happens to be the x value there. And so every single radius is exactly the x value where it is on the graph. And so the beauty of that is we can then just say radius is x value. Does that kind of clear it up a little bit? Okay. So we can choose any cylinder to work with as long as it's in the bound. You mean as sort of like your example one? Yeah, you can draw one wherever. Okay, you can draw one wherever. And so sometimes to sort of like make sure I get that pattern, I draw more than one, but I think it can be really messy. So I would suggest maybe choosing one. So maybe if I were drawing one on my diagram here, I would say something like this. Okay, and so I would say that the height is 2 minus 1, 2 minus 3 squared, because that comes from the equation that we're given, and that the radius is going to be 2. And so we can see that sort of like, if we imagine substitution, everywhere we see an x, we put a 2, that makes the radius and the height of that shell. Is that sort of what you meant, Christina? Or am I way off base? Okay. What do you mean, Thea, when you say, is this applicable to every graph that you'll be working with?
So my understanding is that we have these cylinders, which is where we get the height from. And then when you go down the height and you hit the x-axis, that's where you get your x value from. So if we have other graphs that look like this, where we have a function that is like above the x-axis and revolves around the y-axis, would we still just use x?
Yes, yes.
Does that make sense?
It does.
Okay, cool. Thank you.
Yeah. And David, would it work the same if it was in y? It's going to be very similar, except what do you think the radius is going to be if we revolve it with like, and we have y's in the equation? Like instead of like y equals this, and I had x equals a bunch of things, what do we think our radius might be? Yeah, our radius is going to be a y value. And I'll show you why, because if we go back up here and you imagine that we have our cylinders going this way, the radius is in the y direction this time, whereas the height is in the x direction. Exactly. And so they sort of flip flop, but it is important to keep track of like which one it is and such. Okay. So great observation there. I think that also kind of hopefully answers your question about like, is it always this case? I think that for the context of our class, okay, so let me just give you a few helpful hints, but also things to be aware of. In this class, we are only looking at axis of revolution where there's just like the y-axis, or in a different problem, just the x-axis. In those cases, our radius will just be either x or y, okay? So when we think about writing the equation for the radius, in this class, it will either be x or y, okay? There are situations where it won't just be x or y. We're not going to deal with those in this class, okay? So I just sort of expect us to say, the radius is an x value, so this is going to be x, okay? Or as David is sort of pointing out for some of the questions we're going to take a look at in a little bit, the radius is a y value, so then this would be y, okay? So when you're writing the radius in this class, okay, not always, but in this class, radius should either be x or y. Okay. So I hope that kind of cleared up some of that. All right. I love these kinds of questions. All right. So this one, lots and lots of algebra. Okay. So if you were to sort of multiply everything out, I believe you get x to the fourth minus 7x cubed plus 15x squared minus 9x dx. All right. So if you FOIL everything out or distribute everything out, you should get that. You use a lot of power rule. You plug in your bounds. Many, many steps later, you should end up with 24 pi over 5. Okay. On the exam on Wednesday, I am focusing a lot more on the setup and the decision making. Okay. Setup and decision making. This, I would say, is too gross for exam day. I'm not going to ask you to FOIL out 4 different things and then do power rule and then plug in 1 and then plug in 3 and do all of that. Okay. So the computation piece should actually be much quicker than something like this. But the setup here, when you're studying, when you're doing your quiz 15, make sure you understand how to set things up. Okay. I think it's sort of about half-half. Some of the graphs I did provide for you, some of them I did want you to draw. But if you can plot points, that's always a way. None of the graphs are anything super strange. Lots of sort of square root ones and x squared ones, but not a ton, sort of nothing like this particular one. Like I wouldn't ask you to graph x minus 1 times x minus 3 squared by hand. Okay, but I think it's fair to say, hey, square root of x or square root of x plus 5. Okay, cool. All right, so do we want to do another question right now, or do we want to take a break first? What would we like? Break, please. Great. Okay. So it is 10:25. Let's maybe be back at 10:40. Okay. And that for the last sort of hour and 20 minutes, we'll get through as many examples as we can, and then wrap up this semester. Okay. So I'll see you folks back here in about 15 minutes. So loud. Okay. So example number 2. Okay, so sometimes I wanted to start with example number 1 because I think it's a good way to showcase the fact that sometimes you can only use one method. Okay, so in fact, in example 1, we could not use washer or disk method. We therefore had to have another method. The reality, however, is that most of the time you can actually solve things in one of 2 ways. You could use washer or disk method, or you could use shell method. And so what we're going to take a look at now is an example where we could, in fact, use washer or disk method. That would be absolutely fine, but we're going to use this example to talk about shell method and how that setup might be different. Okay. So this question says, determine the volume of the solid obtained by rotating the region bounded by f of x equals the cube root of x, x equals 8, and the y-axis about the x-axis using shell method. And so you can see here that I am, why is this not working? I am asking you in particular to demonstrate a specific method, okay? Now, I think a lot of us might look at this and say, well, we could definitely use washer method, okay? And if I were to draw a quick sketch off to the side, if we were to draw a quick sketch off to the side, hang on, we're having some technical difficulties. We'll try this one more time. Okay, hang on. I'm going to stop sharing for a second. We're going to reshare. Try it again. Okay, hopefully this will work. Okay, so let's say that we, yes, there we go. Okay, let's say that we had this curve and we had this, and then we are in fact stopping at 8. And if I hadn't told you we were in the shell section, I bet a lot of you would have done something kind of like this to set up for washer method. Okay. Now, if we were to use washer method, we would have our axis of revolution, which would be right here. And which direction would we draw our purple lines? Would they be going up and down, or would they be going side to side? They would be vertical, you got it, right? And so like this would be one purple line, and that purple line is perpendicular to my axis of revolution. And so I would know I would be using washer method. And if we were to think about a setup, we could say volume equals pi, the integral from 0 to 8 of the radius, which is this function, squared dx. Okay. And so I don't know why that's such a weird looking 8, but this would be a setup we could use if we wanted to use washer method. So we could, though, however, as these pictures sort of suggest below, we could set this up using shell method. So same curve and this one, and same reflection, because I'm still rotating it about the same axis. And let's get our axis of revolution here. Where would I draw my, or which direction would my purple lines go this time if I wanted to use shell method? Would they be going up and down or side to side? There you go, right? We would in fact be looking to do this as our setup, our sample purple line. And as we can kind of see from these, graphics below, this does not represent a radius, but rather it represents the height of one cylinder, right? It represents the height of one cylinder. And so I think it's important for us to maybe try this with a few numbers, okay? So let's sort of erase this one for a moment. And let's say that I wanted to choose the skinniest shell, the one that is like right on the x-axis. How tall is that shell? Like, what is the height of that shell? Hmm, 8. Okay, good, good, good. 8. So this one has a height of 8. Now, what if I gave you one here and I told you that this point was, let's say, actually not that one, let's say this one, and I told you that this point was 1, 1. Okay, what is the height of that shell? Oh, 7. How did you get 7?
The way I looked at it was that we have the first one was 8, and that goes from 0 to 8. Like that's the bounds of it, I guess. And then for the next one, you've shrunk the bounds by 1. So I just subtracted 1.
Ah, okay. So instead of jumping right to 7, maybe if we document your thought process, we could say 8 minus 1, which gives us 7. Good, good, good. And let's say that we chose this one. And let's just say that the x value here was like 5, comma something. What would the height of that shell be? Okay. Let's see if Thea's thinking still works. 8 minus 5 gives us 3. Yeah, I would agree. I would agree. Okay. So when we're thinking about our height this time, it seems to me that we have to take sort of our 8, and then we have to subtract whatever this function says the x value is. And so if we think back to our original one, it was 8, but it's really like 8 minus 0, which gives you 8. Okay. Now, if we look at this picture right here, okay, and I think about drawing a sample height of a shell, if let's like rewind to when we learned about area for a moment. If I just wanted to find the area of this green region, I would have to do the right function minus the left function. Right? When we wanted to find just the area, we want to take the right function and we want to subtract the left function, and that will give you the distance across. Okay. Keep that in your heads. We're going to need that when we set up our shell method here. Okay. So we've done this thinking with numbers. We said 8 minus 0, 8 minus 1, 8 minus 5. But what they've shown us here is sort of an algebraic way to think about this. That whatever the x value is, we're going to take 8 minus that x value, or 8 minus y cubed, and that will give us the height of our shell. Now, where are they getting y cubed from though? Because I don't have, like, I didn't get that equation. I didn't get x equals y cubed as an equation. So where is this equation coming from? There we go. There we go. Right. So we have this equation, f of x equals the cube root of x. And we can definitely use that information to use washer method for sure. But if we wanted to use shell method, because our axis of revolution is the x-axis, look at where all of our radii are. All of our radii are along the y-axis. And if we go back to our chart from above, all right, so let's maybe take a little trip back up to that chart. So we've decided we're going to use shell method. Our axis of revolution is the x-axis. All right. Our lines are the heights of these shells. They are parallel to our axis of revolution. That means we're going to be using this formula, 2 pi, the integral from c to d of radius times height. And our radius is in fact a y value. Okay. So let's grab this formula. Let's go back down to example number 2 and see how we can set this up. So volume equals 2 pi, the integral from c to d of radius times height dy. And if we think about which ones are which, we'll have our radius is going to be a y value, or y values, and our height will be x values. Okay, so if we just think about whether things are going up and down or side to side, we'll see that the radius is a y value because it goes up and down, and the height is an x value because it goes side to side. then we can kind of grab information that we have from our equation, okay? Now, I did say before break that for the purposes of this class, the decision I want us to focus on is really on the height part, that because all we're doing is rotating around the axes, that if we have y values here, we can just say that the radius is the y value. So for example, this shell this purple line right here has a radius of 1. Whereas if I drew a purple line here, that would have a radius of 1.5. And if I drew a purple line here, that would have a radius of 0.5. Okay, so every radius of any shell is just going to be the y value where it is. All right. So what that means is I can say 2 pi, the radius will just be the y value. I think we used orange last time. So the radius is the y values. And because our axis of revolution is chosen to sort of simplify this process, it's just going to be the y value. Okay. Now for our height, though, if all we do is change this equation to be x equals, we would be actually just looking at this piece. But we want the distance between these two. So we need to think back to our area and say right curve minus left curve. Okay. In other words, 8 minus the y version of this, or 8 minus y cubed. And so that's going to give us 8 minus y cubed dy as the height. And those are indeed x values. Okay. So let me sort of zoom out for a moment. How are we feeling about where all these different pieces came from? We do still have to fill in the bounds, but how are we feeling about the radius? How are we feeling about the height? Okay, so the 8 minus y cubed. Okay, so let's go back to this picture right here, and the one where you helped us figure out the pattern, okay? So I think you did a great job identifying the pattern in that this was just 8. So it was like this value, which is 8 minus 0. So 8 minus 0 gave us 8. And then we sort of said, let's try a few more samples. And if we can use this sample to help us figure out the pattern, then we'll be able to connect it to the equation. So here I said that the x value was 1, and we did 8 minus 1, and that got us 7, right? And in every single sample we did 8 minus something, 8 minus something, 8 minus something. And so it's 8 minus the x value, but how do we say x? Maybe we should just write it out here, that x equals y cubed, right? That's the equation piece. X equals y cubed, so everywhere I see a 5 or a 1 or a 0, I can replace it with y cubed, and that tells me then the equation for the pattern that you came up with. Okay. That's a really tough jump to go from like the pattern to the equation, but it's a good place to be in to say like, okay, I could see the pattern. Okay. All right. So set up here, if we were to compute it, what should we do about our bounds? So before we get ahead of ourselves, what should we do about our bounds? Any suggestions for bounds? All right, 0 to 8, 0 to 8. All right, what are our thoughts about that? Oh, okay, okay. It is dy. Okay, so it's dy. That means our bounds, just like all the pieces in our integrand, should be y values. So this right here tells you so much, all right? And I've not really seen it in this class. Yeah, I know, it's so tricky, right? There's so many different decisions, but if you have a dy at the end, these numbers have to be y values, okay? So 0 to 2 looks like a good conjecture because I've got a 0 here and I go all the way up to 2, right? That is the biggest radius that I can have for these shells. So 0 to 2. All right. Now, if we were to say compute this, what should we do next? What should we do next if we wanted to compute it? Let's just think process here. You don't have to give me an answer, but you can tell me like, oh, you should factor or you should square, or what is it that you think we should do to this integrand before we open parentheses? Okay. And so what might that be in terms of like a mathematical procedure? Yeah, we could distribute, right? We could distribute, exactly. And so we sort of think about that like these, we get 8y minus y to the fourth dy. Okay. And this, I would say, is a lot more reasonable in terms of something that I would want you to be able to integrate under the time pressures of an exam. Okay. But once you do that, get to the end, and we should get 96 pi over 5. Yeah. All right. So many of these boil down to power rule. And these power rules, right? I bet this power rule, even though I have two different things, might be a little bit easier for some of us than a power rule kind of like this, where we have a fractional power, right? So some people say, oh, I like to use washer method all the time. That's absolutely fine. There might be situations where you are forced to use shell method, but sometimes the efficiency comes in maybe the setup is a little bit harder, but maybe the actual computation piece is a little bit easier. Okay, so that's sort of why we have multiple methods, not just because, oh, well, if this doesn't work, then use that, but sometimes just within them, there's places where we can be a little bit more efficient in our work. Okay. All right. Are we ready for the third example? Maybe. So we got 96 pi over 5 here. Yes. And we've already sort of set this one up, right? The same problem, different method. And so if we think about what we would use for disk or washer method, we had said volume equals pi, the integral from 0 to 8 of my radius squared dx. Okay. How come I don't have a how come I don't have like a big R squared minus little r squared? Like, how come I just have a regular R squared, kind of like a regular, like a filled donut? Yeah, it is filled in, right? And this was like a small piece that I think a few folks missed on the discussion. This purple line, it touches our axis of revolution. All right. And if your purple lines always touch your axis of revolution, then you've got a filled in donut. Okay. There's no hole in the middle, so to speak. All right. And so this one, I would encourage you in your own time. I think this is a really good practice to think about powers, how you use the power rule with fractions. But at the end, you should get the same answer, 96 pi over 5. Okay, so two different setups, right? Washer method, disk and washer method, and shell method. Different parts of it make it messier, right? So I think for some parts, washer method is a little harder. Some parts, shell method is a little bit harder. But knowing how to set it up in two different ways is a really important skill. Okay. And so you should get the same answer for both. So it's kind of like a nice built-in check where you can say, all right, am I getting the same answer or not? Because if you're not, then it's just maybe something in the setup or maybe something in the computation. Okay. All right. Again, a lot of these I think are good practice for you to sort of do as you're studying for the exam. All right. But let's take a look at another example. Okay. So example 4, we've got this function. Okay. So we've got x equals y minus 2 squared, x equals 0 and y equals 0, and we're revolving it around the x-axis using shell method. Okay. Now, not to spoil the surprise, we are going to use this, we're going to set this up for disk method as well in example 5. Okay, so another way to sort of say, let's try two different ways, knowing that we should get the same answer for both of them. All right, so where's my axis of revolution? There it is. Okay, so from this axis of revolution, tell me about the purple lines. Which way should I draw my purple lines, knowing that I'm trying to get shell method? They should be horizontal. You got it. Okay, so this would be the height of one shell. Okay. When we think about shell method, we could say volume equals 2 pi the integral of radius times height dx with x values as bounds, or 2 pi the integral from c to d of radius times height dy. Which one of those should we use in this case? Ooh, so quick. Yes, indeed. We are looking to use dy. Okay. Let's give some justification to that though. How do we know that we're using dy? Okay. I say this one is no. This one is yes, but why? How come? And anyone can answer this. How come we are going to use dy as our setup here? That is always the tricky question, right? Why? How come? How come? Axis of revolution is the x-axis. That is a great indicator. We are looking to use shell method. Yep. And the radii for these shells is the radius along the x-axis or the y-axis? There you go, right? That radius is going Like this right here would be the base of one shell. That's a y value. This is another radius. This is another radius. This is another radius. And all of those are y values. And that's what leads us to say we should use dy. Okay. All right. You've got some more visual pictures here for those of you who really like to see some nice drawn out diagrams. And let's write out our equation. Volume equals 2 pi the integral from c to d of radius times height dy. And before we plug in our functions, can someone remind me why it's a 2 pi in the front? How come it's not a regular pi? There you go, because 2 pi r is the circumference, okay? So in the past, when we think back to like a couple weeks ago, sometimes we had a 2 because we were using symmetry. But this 2 pi comes from exactly like Umar said, is 2 pi r is the circumference, okay? But because they're constants, we're just able to bump them out to the front. All right. So let's sort of set this up a little bit more. 2 pi, the integral from c to d of my radius, we said would be y values. And if we look at the height, this height, that's an x value. And so our height, we can say, is x value. See a question in the chat. Just to review, we use the circumference because the cylinders are hollow. Yes, yes. It's almost like a straw. Like you're thinking about a straw when we think about the cylinders, right? Like a very, very thin straw. And whereas in washer, we use pi r squared because we want the area of circles. Exactly. It comes down to the shape that we are breaking it up into. So if we cut them in circles, we need pi r squared. If we think back to when we were looking at like triangles, before we looked at revolutions, we were looking at like, what if there was a triangle? We used 1/2 base times height. Or if we're looking at rectangles, we used base times height. If we looked at a semicircle, we used pi r squared over 2. So it all comes back to the idea of area. Yeah, you're right. You are exactly right. Okay. So 2 pi, my radius, what can I write as my radius? I know my radius corresponds to y values, and how can I sort of accommodate that in the equation? Absolutely. We've got the radius as the y value. Perfect. Okay. Now remember, this is something only true in this class, only true because our axis of revolution is right along the x-axis. Okay. All right, the height of our shell. Let's look back at our diagram. My height is an x value. I have an equation, and let's think back to our like area. When we were looking at area sort of like sideways pictures, we had to do our right function minus the left function. So I say that we have our right function. What is our left function? Like, what's the equation for this? Super close. There we go. X equals 0, x equals 0. And so we have this x equals 0 part. So if we want to find this height, we could say y minus 2 squared minus 0. And so we can grab that equation, y minus 2 squared minus 0, and that's going to go in for our height. So height will be y minus 2 squared minus 0. Let's put brackets around that just so we know everything in there is our height. Okay. Now, I know it's sort of silly to write the minus 0, but if you've been with me all year, you know I like to look for the bigger pattern, right? Because it seems like sometimes we subtract and sometimes we don't. But I think the reality is we're always subtracting. It's just sometimes that second number is 0. So it doesn't matter if we write it or not. But like right minus left, that's what we did here, is the same as, where did it go? We had our right minus left over here, right? So if you kind of think, I always have to do right minus left, or I always have to do top minus bottom, just sometimes one of those is 0, I think that'll keep you from making that mistake of like, do I have to subtract or not? Okay. So if we are looking at a sideways situation, we do want to do right minus left. And even though this is a different picture, we can still do right minus left. Okay. All right. So this one, if we wanted to actually calculate this, let's actually find our bounds first. So what are our bounds for the radius? In other words, what is the smallest radius that we could have? So if you look here, what might be the smallest radius that we have? Like the skinniest shell. X equals 4. So x equals 4 would be like here, that's the height of the shell, but what's the radius of that shell? 0. Okay, so 0 is the smallest radius. Okay, what is the biggest radius we could have? 2. All right, right. And remember, if you're like, I don't really understand where people are getting these numbers from, this is dy, so our bounds should be y values, right? So we're going to go from 0 all the way to 2, and that will give me all of the shells in the region I'm interested in. Okay, so 0 to 2. Now, I think, again, this one is probably a good example of something I might not ask you to get so computation heavy on the exam, right? Because if we were to expand this all out, we might get y cubed minus 4y squared plus 4y dy, 4y dy. Power rule, no fractions. So we just got to plug in 2 and plug in 0. And at the end of the day, we should get 8 pi over 3. Okay. So shell method, we get 8 pi over 3. If we use washer method, what should we get? If we were to use washer method to find the same volume, what should our answer be? Exactly, we should get the same answer, right? And so let's talk about the setup for if we were to use washer method, okay? Before we do that, are there any questions that folks have on the setup of this example, where different things are coming from? Okay, so example 5, we've got the same exact question, but now let's use disk or washer method. Okay, so let's draw in our axis of revolution. Which way should I draw my purple lines here if I want to commit to using disk or washer method? Should we still depend on about the x-axis or about the y-axis for the axis of revolution? Yeah, so whatever this is, like wherever it says about the whatever axis, that's your axis of revolution, yes. Cool. All right, so if we were to use disk and washer method, what relationship should our purple lines have to our axis of revolution? They should be perpendicular. Great. So we've got like something like this. All right. And if we imagine a few of those, we can see that we're stacking our circles along the x-axis. Okay. All right. Now, let's be more specific. Should I use disk method or should I use washer method? And how do I know? Okay, disk or washer, which one should I use? Yeah, exactly. So sometimes we find some language that works for us, like donuts, right? Regular donuts, filled in donuts, but we still want to be able to root this in the vocabulary that other people would maybe also understand, right? And so when we think about disk method, we're thinking pi r squared. And just like Graham said, there's only one radius. There's no sort of inner radius. However, if we were to use washer method, that's the same thing as saying pi big R squared minus pi little r squared, right? And so if you're having discussions, mathematical, nerdy discussions with folks who were not in this section of Math 150, you might want to refer to things as disk method or washer method, right? And so I agree. I think in this case, we are going to use our disk method and we are not going to use the washer method simply because our purple lines, every single one of them, they touch my axis of revolution, okay? All right, that's one decision to make. Now, should it be volume equals the integral of area dx or volume equals the integral of area dy? You know, if you were going to Stanford for a math doctorate, though, you would probably also be TAing or teaching sections of Calc 1, and I bet your students would definitely relate to that. What's confusing? I'm sure a lot of this is confusing, but what's sort of immediately confusing? For example 2, we use the disk use. Okay, let's go back up to example 2 for a moment. So example 2, okay, I see. So example 3, okay. So we didn't explicitly state, right? But we said disk or washer method. So actually looking at this setup, did we use disk method or washer method? Yeah, exactly. So we could say that this is disk method, which honestly, probably you could even say disk and washer method are sort of the same, because you really have like pi big R squared minus pi little r squared. If little r equals 0, then you have a filled in donut, and now you have disk method. So sort of kind of silly to have two different names for it, where one of them you subtract something and where the other one you subtract 0, but they're essentially the same. Okay, thanks for clarifying that. Okay. Oops. All right, so we've determined disk method because our purple lines touch our axis of revolution. Do we want to do dx or do we want to do dy? Yes, I agree. We want dx and not dy because exactly stacking along x-axis. Exactly. Okay. All right. So we sort of made the important decisions. We know we're using pi r squared. We know we're doing dx. That means our volume should be pi, the integral from a to b of radius squared dx. All right, so all of that decision making led us to this particular formula. So what do we want to put in for A, and what do we want to put in for B? I love it, 0 to 4, right? Because we want these to be X values, not Y values. Okay, what are we going to put in for the radius? What are we going to put in for the radius? Y minus 2 squared. Okay, so y minus 2 squared. Ah. Okay. Okay. So I actually, Thea, love what you said, because yes, that defines the radius. Okay. And in the form it's in, we are indeed mixing x's and y's. Okay. And so you've identified the correct function, but we have to rename it. We have to rename it so that it has x's so that we can integrate. Okay. So let's rename. We've got x equals y minus 2 squared. How do we rename that? Oh, I don't know, salty donut. I've tried those like the ones that have the bacon on the donut. I think that's actually pretty good. Oh yeah, bagel. How do we rename this though? How do we get this to be y equals instead of x equals? Because then life would be great. Okay, so let's get rid of that square first. So we get square root of x equals y minus 2. Okay, and then we're going to add 2, so we get y equals square root of x plus 2. Okay. Now, this problem has a small twist to it, okay? Here's the twist. If we think about sort of a square function, we really have like something like this. Now, I don't have the top half of this sideways parabola. I only have the bottom half. Since I only have the bottom half, I actually want to have negative root x plus 2. Okay. Anytime we take a square root, we really need to consider plus and minus. We need to think in particular what sort of matches with the diagram. Okay. And so when we think about a sideways parabola, if we had the top half, then this would be all fine and good. But since we have sort of the bottom half of this parabola, we need to make sure we have that negative sign there. Okay. And so now that we've renamed it as negative square root of x plus 2, now we can get our equation so that everything matches. 0 to 4 of negative root x plus 2 squared dx. Okay. Now, I hope all of this sort of like, what kind of mistakes would we make, don't actually lead you to make these mistakes. But if we were to highlight maybe the most common mistake in simplifying this, what do you think that might be? Yeah, not doing the 2ab. So I can imagine someone doing x plus 4, right? And that we would say did not distribute. And I bet when you got to the end, you would not get the same answer we got using shell method. Okay, so you want to be really careful about your simplification. And at the end of the day, you should end up with your 8 pi over 3. Okay. Now, even though disk and washer method is something that we've sort of, been working on longer than shell method, I think that in this case, disk and washer method is a little bit trickier to set up than shell method. Okay, but that's sort of like my personal opinion. You may find that both of them are equally accessible, and that's totally fine. Okay. All right, let's do maybe one more question. And see how it goes. All right, so question number 6 says, determine the volume of the solid obtained by rotating the region bounded by y equals 1 over x equals 1/2, x equals 4 and y equals 0 about the y-axis using shell method, okay? So you've got a diagram down here that has sort of a more three-dimensional look at this, but take a moment and think about two important decisions, okay? So one of them is thinking about whether where your purple lines, like what sort of direction they're going in. And the other one is thinking about whether you should have dx or dy, okay? So take a moment and think about those, and let's see what we get. All right, and when you were done, maybe send me a message that says what your thoughts are on those two things. Right, I still see quite a few folks are thinking. If you're thinking about answering those questions, number one, the purple lines, are they going horizontally or vertically? And number two, should you choose dx or dy? Right. So we've got some A lot more answers now, which is awesome. Let's see what we think. All right, so purple lines. Maybe before I do that, if I highlight my axis of revolution, and I know that's the y-axis, and since I'm using shell method, those purple lines have to be parallel. Okay, and you can almost think, if you want to know, like if you're writing the parallel in math, like if we do this, this means perpendicular, but if we write this, it means parallel. And check out what the two last letters in shell method are, right? So the lines that you draw should be parallel to that axis of revolution. Okay, and since we are using shell method, the purple lines should be parallel to the axis of revolution. Okay, so that right there makes that decision for you. Okay, so if we were to draw one, maybe having one like this, all right, that would be a sample height to a shell. This would be another height to a shell. This would be another height to a shell. But if these are the heights, where's the radius? Because the radius tells us the dy or the dx. Okay, so which direction is the radius, or what kind of values are they? So the radius, well, let's see, this is not the radius, right? This is the height of the shell. Where would we find the radius of the shell? So this would be the radius, right? This is the height, but this down here is the radius. And as soon as we see that our radius is x values, so we choose dx. Okay, so let me say that one more time. If we're using shell method, okay, once you've drawn your axis of revolution, your purple lines have to be parallel. Okay, so the last two letters in shell, LL, we're thinking that's very similar to the math symbol, that they're parallel. And so we draw these lines immediately. Now these lines are the heights. So if the y value is the height, that means that the x values are the radii. And once we get the radius, that helps us choose our dx or dy. Does that make a little bit more sense? I know it's a lot of decisions, but again, I would encourage you to practice that decision-making piece. If you don't like if the chart that I showed in the notes isn't making too much sense, make your own chart. Okay, make a flow chart. Like, how do I know when to use what? That could be a great study activity, actually. Okay. So if we look at sort of this diagram here, we can see that we've got our height is defined by the function, whereas the radius is just the x value. Okay. And since we have our x values, we want to use dx And so our volume equals 2 pi, the integral from a to b of the radius times the height dx. All right. Now we know from our diagram it's 2 pi, the integral from a to b of the x values as the radius, the y values as the height. And we only know that because we know y values go up and down and x values go side to side. Okay, so that part doesn't change. When we finish this off, we have 2 pi. My radius, I can say, is just x. My height is my function, top minus bottom, 1 over x minus 0, because I happen to be looking at the y or the x-axis as the bottom piece. Okay, so you don't have to write the minus 0, but if it helps you remember top minus bottom or right minus left, that's not a bad thing. And the final piece we need is to determine the bounds. And so looking at the pictures, what is the smallest radius that we have? Like, what is the skinniest shell that we can have? 0.5. Good, good, good. And that would be the one that is like right here. It happens to be the tallest one, but it's also the skinniest one. And what is the largest radius that we can have? 4. All right, and that would be the one all the way out here, and I can't draw because it would go off my page, but I would basically have something like that. Okay, so the smallest radius is at 0.5, the biggest one is 4. Those are our bounds. So 1/2 to 4. And I think you'll find that this one works out very nicely once you simplify. You'll end up with 1/2 to 4 of just 1 dx. And so you won't have that many things to plug in or that much integrating to do. You should end up with a volume of 7 pi. Okay. So let's put that all on one page so we can kind of see that. All right. But it seems to me that a great place to focus some of that studying time might really be around those two questions. My purple lines, which direction should they be? And is it dx or dy? Okay. And so I think we'll finish there. So I'm gonna stop sharing my screen. And